Just to let you know, we are also recording these activities, so the course, and so will be available after the meeting. We just take a couple of minutes and then okay. I think we can just start with welcoming you all, and then we have still time to admit those people who are arriving. Thank you for coming. I'm Silvia Bodoardo from Politecnico of Torino, and I'm welcoming you to this zeroing course. That's an activity that was carried out under SENSIBAT project. SENSIBAT project will be fully presented tomorrow by the coordinator, which is Inigo Gagnaga of Ikerland. And we are going to give this activity under SENSIBAT project, which I thanks, of course, and also we under the Butter 2030 umbrella. So it means that we are a very big community involving a lot of people in Europe. And then I also thank Daniel Brandel, who is here in presenting Butter 2030. And of course, I really need to thank, first of all, Professor Garke that represents Varta here, who really set all the activities under this zeroing course. So the agenda is here presented. I think you can see my screen. First of all, we have just these few minutes to welcome everyone. Still people are arriving. I think we get a good success before starting, as we got more than 200, 230 registrations. So it means that these activities in Europe are really welcome, as education is one of the milestone also under Butter 2030 project, as we really need to get many people skilled in Europe in order to work in this so big field, brilliant field, let me say, of batteries. So today we will have the presentation of battery 2030 given by Daniel, that is already here. I will start with a very short introduction of lithium-ion cells, so what is at the basis of this technology. And then we will get the remaining of the day dedicated to overview of the state of batteries and the processes influencing lifetime states. Those are given by Professor Jürgen Garke. At the end of the day, we will have a question and answer session. So please, if you have any question and so on, write them even during the presentations on the chat. So at the end, I will select eventually if there are many. If not, of course, we will be very happy to answer to all of them if able to do. and that will be an more interactive activity at the end of this day, and the same will be tomorrow. So tomorrow will be a little bit deeper in the topic. So we will have a presentation about sensors for measuring battery states, how to calculate and measure those battery states. These two lectures will be given by Ikerland, by the Inigo Candiaga, which is the coordinator of the SENSIBAT project, and also by Michael Jank of Fraunhofer Institute. After this part, we will get again a question and answer session. And finally, the day will end tomorrow with more practical examples on how sensors can be implemented in cells, and which are already some practical example of activities run under this project. So also showing the importance of the use of those sensors. So we will get a lecture of Andrea Marchese of Polito, reporting modeling with sensor, and one practical example, and how implement these models in BMS, and this is given by Flanders Make, Joris de Hoog. So thank you very much for being here. I hope that you can have a good course and a good time in here us. And so even if we are a few minutes in advance, I think I can give the floor to Daniel Brander, which is representing Christina Estrom today also, which she is the coordinator of this project. So please, Daniel, thank you for being here, and the floor is yours. Thank you.
Thank you very much, Silvia. I will try to share my screen.
There's an arrow up in your screen on the... Okay, perfect. We see it. Thank you.
You see it? That's
yes,
excellent.
Perfect.
And I will try to put this in presentation mode as well.
Great.
So, good morning, everyone, and thank you for the introduction, Silvia. As said, my name is Daniel Brandell. I come from Uppsala University in the interesting country of Sweden in Northern Europe. And actually, I'm substituting today for Christina Edström. Christina is a colleague of mine, and she runs this Battery 2030 Plus CSA activity, coordination and support action. That is the real umbrella of Battery 2030 Plus. And we are very happy that we were invited to present a little bit about Battery 2030 Plus and our ambitions in this meeting. SENSIBAT is a key project and a vital part of the Battery 2030 Plus ambition. And we are very impressed by Silvia and SENSIBAT also for organizing this course and these activities. We're all on a little bit of a learning phase when it comes to the implementation of sensing into batteries. And I think this will be a very rewarding workshop, listening to some of the very true experts in these areas during these days. For those of you who have not heard about Battery 2030 Plus, what is Battery 2030 Plus? Well, this connects this initiative with the European mission to contribute to a carbon neutral society. And with a carbon neutral society, we need a lot of replacement of the fossil fuels, both in the electric grid and within the transportation sector. And for this, we need energy storage. And energy storage can be batteries, and this I think we all know. So the ambition here of Battery 2030 Plus is a little bit to put Europe, especially, in a very good position by the year 2030 to really be a key player internationally when it comes to battery fabrication and to battery implementation. And this means that since the technology is far ahead of us, it's still 8 years to 2030, there is quite a lot of research, academic research, industrial research, development work that needs to be done in order for us to achieve this goal. So what we need to do is to reinvent the way that we invent the ultra high performance batteries of the future. And this means also that we need to accelerate the discovery of new materials and new battery concepts, and also that we add smart functionalities to the battery cell. Sensors is one of these smart functionalities that we foresee will be implemented in the batteries of the future, but we still need to explore and do this in the right way. We always need to keep manufacturability and recyclability in mind when we are doing this. So this is the main ambition of this large-scale project. Why we have taken this initiative, or why the European Commission has taken this initiative to launch this very large-scale effort, is naturally connected with the societal development that we all foresee. We see a real increase in global battery demand. We are talking about more than multiplying the production with a factor of 10, maybe even more than that. And we can also see right now battery factories, so-called gigafactories, popping up more or less everywhere around the European continent. And in order for these to be sustainable and to have a good prospect and be able to compete internationally, they need to be super good batteries that are manufactured. And this means also that quite a lot of research and development is necessary for Europe to take this world-leading position. The European Green Deal was presented in December 2019, and it sets out how to make Europe the first climate-neutral continent by 2050. This is a super ambitious goal, but we need to reach this goal, and this is a part of reaching the goal. This also needs that all these type of research activities that we have around the European continent, and also looking out to what is happening at other places in the world, they need coordination, and it needs also that we do things together and strive together to reach this goal. And therefore we need these kind of umbrella initiatives like Battery 2030 Plus. So Battery 2030 Plus is a pan-European large-scale research environment that is working together to implement the goals that we have set out in a roadmap. And these are the goals that I just mentioned. The initiative today comprises of 7 different projects, and it involves quite a lot of academy, research institute, and also industry. We have these 7 projects. We have Big Map, which is focusing really on the combination of computational exploration together with artificial intelligence and machine learnings, and also connecting this with key experimental techniques in order to create a platform for materials discovery acceleration to better map and try to predict the behavior of novel materials that will be implemented in these future batteries. It's also connected very much to understanding the interfaces in the battery. BIG stands for the battery interface genome. And the interfaces controls a lot of the performance of the battery, but also the safety and the aging. And therefore it's vital to understand this. And this is something that we foresee that this project will bring. We have 3 different projects on sensoring. SENSIBAT is one of them, but we also have Spartacus and Instabat, working on the implementation into battery of different types of sensors. And this is something that we will hear much more about during this 2-day workshop. There's also 2 projects on self-healing, Hidden and Bat Forever. Self-healing materials are materials that are very novel to try to implement into battery system, but they are supposed to heal the battery chemically when something is happening that is destroying or disrupting the battery from its normal functionality. If we look at where these projects are situated in Europe, we have the coordinators of all different projects pointed out on this map. They are from Finland, from Denmark, from Germany, from Belgium, from France, and from Spain. And all these stars that we have here, they represent other countries involved in these different projects. So we see that there is a good geographical coverage across the European continent. In the future projects that will come out of Battery 2030 Plus, we of course hope to involve even more partners and also even more of the geographical diversity, so that we all work together in order to reach our ambitious goals. So if we look at our main aims, this is really to invent the ultra high performance batteries that are both safe, affordable and sustainable, and that also has a very long lifetime, because lifetime is also very much connected with the sustainability. Sensing, that we will hear more about, and these smart functionalities is also a key in order to understand battery behavior, to prolong the lifetime, and also then to make an impact on the sustainability of the entire battery cell and system. This is also a part of providing these new tools and breakthrough technology to the European battery industry and throughout the entire value chain of batteries, from the cradle to the grave. But it's not really the grave, because we also have to keep recycling as a core technology for sustainability. The ambition here is to enable long-term European leadership in both existing markets like transport and stationary storage, but also quite a lot for future emerging applications in robotics, aerospace, in medical devices, Internet of Things, etc., where we also foresee a boom in different type of electrochemical energy storage devices. The roadmap is then quite ambitious, making Europe world leading in these type of technologies and really accelerate the invention of new materials, new cell concept, new cell chemistries within this time frame is a gigantic undertaking, but it also connects with all these goals of making Europe a climate neutral continent. Today, we have these overarching research teams that are 3 and 6 research areas that are needed to invent the sustainable batteries of the futures. All areas also have short and mid and long-term goals. So there is very clearly a good roadmap on how to accelerate this development, and in order for us to check that we are reaching the milestones and the key performance indicator that we have formulated. This is in the accelerated discovery of battery interfaces and materials, the big map. In the integration of the smart functionalities, the sensing and the self-healing, and also then in the cross-cutting areas of manufacturability and of recyclability. Battery 2030 Plus has adopted what is called a chemistry neutral approach, and this is quite an interesting and inclusive way of looking at battery discovery, because Battery 2030 Plus does not dictate what kind of materials or concepts or cell chemistries that Europe should produce and should be world leading of. It's much more so that Battery 2030 Plus sets up an ambition for how to make things ultra high in performance, but also very sustainable and very affordable. And the cell chemistries that can actually fit all of these different criteria are the ones that will actually survive and be large scale implemented into our energy systems. This means that what we focus on is quite a lot of lithium battery chemistries, both generation 3 that we have today, advanced lithium ion, and then generation 4 and 5 of the lithium battery cell chemistries. Generation 4 is then primarily solid state batteries, also with lithium metal, while generation 5 is looking even beyond this with lithium air or lithium sulfur. We also envision to study or do study quite a lot of post-lithium battery chemistries. This is based on, for example, sodium ion, potassium ion, multivalent metal ions, metal air batteries, redox flow batteries, etc. This is also part of our roadmap. And then also to include future battery chemistries, what actually comes after the generations of batteries that is very low technology readiness level research today. So we formulated this roadmap both in short-term, medium-term, and long-term goals. In the short-term goals, we have the project that is currently running in developing theoretical and experimental platforms and tools. The next step that we are now looking into, and which will soon happen, is the integration of these different parts so that there is a key combination of materials discovery, of sensing, of self-healing. And then the long-term goal is to unify all of these concepts in order to actually produce these ultra-high performance batteries and understand their chemistries and their materials on everything from electronic level up to cell level. This undertaking is quite extensive. It involves a lot of industry association within these projects. And this is actually trying to cover the entire value chain of batteries, from raw materials to battery cells and systems, and then to the application of batteries, and then to recycling in order to close the loop. And we have very many different European companies that we are at interplay with throughout this entire value chain, and that will be necessary in order to actually achieve these future batteries. We are organized in the following way: that Battery 2030 Plus has a core group of a number of different partners. We have Uppsala University up in the top left, but quite a lot of other universities and also research institutes. Then we have quite a lot of supporting organization around us, competence centers and other type of research institutes and organizations that also are focusing and organizing this, often at the local level or in parallel, but with another type of conceptual understanding and ambition than maybe focusing only on the battery development. This is part of a very rapidly growing and complicated European research and innovation landscape for batteries. Battery 2030 Plus is not the only organization, but it's one that is really focusing on the long-term research efforts in order to advance. But then we might have heard and might be aware of or might be member of other organizations that are also at the interplay in this local landscape. And these are organizations that are not competing with each other. We have different perspectives, different ambitions, and a little bit of different methods and functions. And it is the interplay between these different organizations that will be actually a key to be successful in this development. So I hope that this gave you some insights into Battery 2030 Plus and what this is all about. You can of course read more at our webpage and follow us on Twitter or on LinkedIn. And that was all for me. Thank you very much.
Thank you very much, Daniel, for this very clear overview. It was very important as both SENSIBAT, but also the frame, the European frame of batteries is starting from new ideas and disruptive thinking coming from Battery 2030. So it was very important to get an overview before starting this course, which is basic, but is the base on which we are working for getting brilliant, as I told before, future in this field. So thank you very much, and keep posted, and let's see soon. Thank you, Daniel. So now we move to the first part of this course, let me say. I hope, oh, sorry, I was wrong. I wanted to open this. Good. So now we are, after the presentation of Butter 2030, I will give you a very short and simple introduction of lithium-ion cells. Before that, I will give a very short introduction about our activity in Torino, so where I'm working, our electrochemistry group. Then I will report something about lithium-ion cells principles, production of lithium-ion cells, cell structure, cathode and anode and electrolyte materials, and then a really few slides on what is going for future toward all solid state chemistry, and finally a short summary of everything. So very briefly, I'm working in Polytechnic of Torino. We are we are a university which is giving and skilling new architects and engineers only. And within this more technical university, we have the electrochemistry group that is quite big compared to the Italian landscape, but not so big, let me say, in the European one. We are more than 20 people now, and we are mainly working on advanced materials from TRL 3 to 7, so going to scale up the production of the advanced materials to the till arriving to the industrial testing, and also the thermal testing and so on. And of course, big part of our work is in new future and emerging technologies based on solid state, post-lithium ion technologies, hybrid system, and lithium sulfur, lithium air, metal air, and so on. And also, of course, as you can see here, self-healing properties of materials and integration of sensors. Just to conclude, we have a task force in Polytechnic, which I'm proud to lead, as we have expertise in the whole field of engineers. We can cover from materials, nanosensors, new cell designs, to all modeling, both as we, for example, I'm involved also in Big Map and in several projects on modeling. And then the integration, battery assembly, integration of batteries in electric vehicles, and also for stationary application, finally arriving to LCA and recycling. Good. So coming in the deep of this presentation, I just recap few basic concepts, very simple basic concept. We have principally, we have three different kind of electrochemical power sources. The first are primary or voltaic cell. These are not reversible system in which reactants can only transform in products, and there's no way to get them back, producing again the reactant, recharging the battery. So this is not rechargeable cell, and when reactants are fully transformed in products, there is no other possibility to get additional energy. Secondary cells, that we also call batteries, are reversible system in which reactant can be transformed in product, and then and this transformation produces electrons, of course, that we use in order to get energy, electrical energy in particular, but we can also use current in order to transform back products into reactants. So this is very important, and of course all the capacity or the amount of energy contained in a battery depends on the amount of reactant then that can react. There's a third system that are the fuel cells. In fuel cells, the electrochemical reactor is not dependent on the amount of reactant and the amount of product that are outside of the electrochemical reactor. So we have reactant that are going inside the electrochemical reactor. They react, produce electrons, and then we will have product going outside. The typical fuel cell is the hydrogen fuel cell, PEM fuel cell, which uses hydrogen and oxygen as reactant and transform them inside the electrochemical reactor, getting products. Of course, this system can work until you are feeding it with the new reactant. Well, just to remember, we are speaking about batteries. I don't know if you can, I hope you can also see my arrow. Batteries have commonly much lower volumetric and gravimetric energy density, specific volumetric energy and specific energy compared to the system we are used to use today in the combustion engines, so both gaseous fuels and liquid fuels. So we have to keep it very well in mind, as at the present we cannot get the same number of kilometers, let me say, run with using batteries as the one we can have in liquid fuels. But liquid fuels cannot be, or liquid or gaseous fuels are not renewables, and so as a consequence, of course, they are going to conclude, and then we, of course, unfortunately, we are leaving this period in which the amount of the gases and methane coming from the eastern countries, it's really critical, and so on. So commonly, the main typical cells and batteries we are using are based on lithium. Why? Why lithium? So lithium, of course, is the first metal in the periodic table, is the element number 3, and it's the lightest element, metallic element, of course, of the periodic table, and it has a few big important advantages. It is very reactive, but it presents the lowest standard electrode potential, that is -3 versus the hydrogen electrode, and a very huge capacity, which is around 3,800 ampere hour per gram. If we compare lithium, the specific capacity and the standard potential of lithium, you see that there is no other cations that can compete in somehow with it. Of course, then we have other issues that are related to abundancy and so on, and that also can give opportunities also to other cations such as sodium, for example, but also potassium, whose voltage is quite close to the one of lithium, even if the specific capacity is lower. Good. Let me show you very simply how a lithium cell works. Here we are speaking about lithium cells. The lithium cells is using metallic lithium as anode, and as a cathode we have a ceramic compound, let me say, that can be an oxide commonly, or a phosphate, or any other material, which is composed by oxygen, if it is an oxide, of course, which is the negative part of the molecules of this compound. And then the other elements are lithium, of course, and transition metal. Let's consider, for example, that the transition metal we are taking into consideration inside here is as an oxidation state like plus N, for example. During charge, we have the oxidation of the metal, which increases its oxidation states, as an example, from N to N plus 1. And as the negative charge remaining on oxygen is not changes, of course, in order to still keep the electroneutrality of all the compound, one lithium ion is eliminated from is they intercalated from the compound, and together with this we have the production of one electron that is used in order to produce electrical current that passes outside the cell. This is the charge. Of course, during this charge, we have the opposite, and of course, the transition metal reduces oxidation states, forming again the previous compound and reinserting lithium ion inside the cell. If we have metallic lithium as an anode, lithium ion are of course reduced at the anode during charge, producing metallic lithium, and are oxidized during discharge, of course, producing lithium ions. Why lithium? If you check, you can see this is the typical, let me say, series of potential in which we are reporting the electrode potential, and as a we use as a reference the hydrogen electrode, whose voltage is given as 0 volt. If you check, lithium is the element with presenting the lowest voltage. And if you compare the the difference in voltage you have between lithium or graphite, as I will say immediately after, and the most common cathode material, you have the wider voltage. You cannot get the same wide voltage, high difference in voltage as in the case of, for example, nickel metal hydride batteries, or if you are taking into consideration lead acid batteries, for example. So the possibility to use lithium or graphite give us the opportunity to increase the voltage, and as a consequence, the energy density of the battery, which is one of the main parameters. Of course, just to say, if we also can increase a bit the voltage, we are going to increase this difference in voltage and again the energy density. So for example, the use of oxygen in lithium air batteries really interesting, because we have very light elements and we can have energy density, theoretical energy density, which can be even 10 times the one of lithium. Or to use sulfur, which as a cathode, sulfur as even if the difference in voltage is much smaller, but sulfur can use 2 electrons, and this double the capacity of the system, and as a consequence again their overall the overall sorry energy density. And here is lithium nickel metal oxide is another example. It's NMC without graphite, whose voltage is higher. So we are going to look cathode material which always with higher and higher voltages. Okay, so we spoke about lithium cells. In 1991, Sony commercialized the first lithium-ion cell. The difference between a lithium cell and a lithium-ion cell is related to the use of graphite instead of metallic lithium. Graphite, of course, instead of getting the reduction of lithium ion inside in to form a metallic lithium, in this case is graphite who is reducing, and the lithium ion are moving toward the electrolyte and will be inserted inside the graphite electrode. So that the advantage is that we never have metallic lithium in the cell. You know that, as I told already in the beginning of this presentation, metallic lithium is very reactive, and as a consequence, it's also quite unsafe. In this case, lithium always remain as lithium ion, and as a consequence, the safety of the whole system is much, much more important. Let me also remember that a full cell is not only composed by simple graphite and simply the active material, but we have a lot of other elements. As an example, we need, as both graphite and also the cathode are powder, they cannot stay alone, just attached directly to the tabs, but they need to be attached directly on some more uh, robust elements, which are the current collector. The current collector are commonly copper for the anode, and they are aluminum for the cathodes. Of course, we are speaking about a porous system, and the anodes, as I will show you in a while, and also the cathode are mixture between the active materials and also carbon-based additive that are used in order to assure the electron movement inside the wall surface and the wall thickness of the cathode and of the anode, and they are porous, as you can see here, in order to let the electrolyte to move and to reach all the particles of the cathode. Between the two, between the anode and the cathode, there's also a separator that is used in order to avoid short circuit, and also in order to absorb the electrolyte, and that is also then um, inserted in both of the other electrode. So we have two mechanisms to take into consideration. On one side, we need to get a good electron movement from the anode to the cathode during discharge, of course, and this has to be assured thanks to the current collector, which are very good electron conductor, but this is also to be well assured also from one particle to another particle in the electrode. So on one side, we need to get this movement of electrons from particles, and on the other side, we need to get also the movement of lithium ions that is assured only inside the electrode, the liquid electrolyte in the case of common, let me say, the most common lithium ion cells. So the system should be porous enough in order to assure a good wettability, and so that the electrolyte can move properly inside the electrode, but it has to be dense enough in order to assure a good transport of electron from one particle to the other one. So we have two double movement, electrons on one side and mass from the electrolyte in order to assure the lithium ion. So here you can see in blue the active particles. These, let me say, movements and the path of the electrons from the current collector to reach all the particle is assured thanks to the use of carbon black, which is an additive, uh, so that electrons can move through carbon black and reach each of the particles. And on the other side, we have lithium ion movement. So just to remember, one cell, which is the one you can see here on the left-hand side, is composed by a stack of different electrodes. These electrodes are anode on one side, the cathode on the other side. You can see here are the anodes, here are the cathodes, and between the two we have a separator, which is a plastic sheet, a piece of paper that can assure a good transport of lithium ion that are here the electrolyte. Very briefly, as time is running very fast, the production of a lithium ion cell passes through different steps. The first step is the mixing of the active material with the carbon black, as eventually additives, and of course a binder. The binder is used to keep the particle attached one with the other and then on the current collector. Then we have the coating, so that the slurry produced by mixing is deposited on a film that is of the current collector moving through a evaporating chamber. Then is compressed thanks to a calendaring system all the exceeding part, the metallic exceeding part are cut in this lithium machine, finally dried. Then we are attaching the tub to welded on the current collectors, and then we have the stacking: one cathode, one anode, one separator, one anode, one separator, one cathode, and so on. Everything then is packed, filled with the electrolyte. And then after aging, we have the formation of the electrolyte of the cell. Those aspects, even I just passed through, are still all these each of the step are really very, very important, and has to be discussed and followed really careful. So even in Battery 2030, there are a lot of activities also in reducing the energy step by step, and rethinking also on the production of lithium-ion cells. There are different format. I will really. There are the pouch cells. They are the one you already saw in previous slides, in which the electrodes are stacked one on the other side, or we have winding of the electrodes that are rolled around in a cylindrical cell, or finally in a prismatic cell. So there are different format, different application. For example, pouch cell are much softer and lighter in somehow. Cylindrical cell are harder due to the case, which is much harder. The same for prismatic cell, of course, depending on the need, and we can have different format, different distribution of heat during working of cells, and so on. Speaking about material, we have in view of principle, three main types of materials. The insertion materials, that are the one most commonly used in lithium-ion cells. They can be homogeneous or heterogeneous. There are materials in which lithium intercalates inside the layers or inside the lattice of the cathode in a homogeneous or in a not homogeneous way. It's of course depending on the material cell. Then we have alloying in some of the elements, as silicon, for example. Lithium is inserted inside the lattice as metal, and this makes strongly to change the volume of the cell. So we have a very big volume expansion of the material that has to be taken carefully into consideration. But those materials are commonly very large capacity materials, and this is very important. So on one side, very important aspects like large capacity, on the other aspects, a big issue related to volume expansion. And finally, conversion systems that are still under development, but there are a lot of efforts under those because of the large capacity of gain of these materials. Conversion systems are systems that really are changing during charge and discharge. If we speak about insertion material, the materials itself is not changing its structure. But simply you have the change of the oxidation state of the metallic element. In the case of the conversion, you are passing from one form to another one. For example, sulfur is a conversion cathode, which changes from sulfur to lithium sulfide at the end of its charge. So what is happening is that there can be a volume change again, as in not so big as in alloying, but still can be important, and a voltage hysteresis that should be reduced as much as possible, and this is everything is under study, of course. Just to give a short overview of possible insertion materials, here we have simply reported the main ones. One very important is lithium iron phosphate, that is commonly reported as LFP. You can get it and find it in all the data sheet in this way. This is a very interesting material because it doesn't change. It's a zero strain material on one side. On the other side, the chemical bonds are very, very strong. And so it doesn't change during cycling. It can also be used, for example, for power applications. Then we have a lot of materials that are layered structure, like the historical one, LCO, that is lithium cobaltite. Lithium cobaltite was the first commercial cathode material that is not more used because of the big amount of cobalt used in the material, and sustainability is another issue on which we have not time at all to speak about. Then we have all the NMC, which are a big family of materials that are containing nickel, manganese, and cobalt, with reducing time by time the amount of cobalt. Now the commercial one is 811 with 80% of nickel, 10% of manganese, and 10% of cobalt. And then, and finally, spinel structure, like, for example, lithium, the spinel lithium manganese oxide, or titanates that are mainly used at the anode. Good. So if we are speaking about cathode and anode materials, of course, we need to get cathode, which are the element with high voltage. Higher is the voltage, higher is the difference in voltage of the whole cell, and higher will be the full energy density of the cell itself. On the other side, we have anodes. So anodes have to have a very low voltage, but ensure a very high capacity. So metallic lithium, as you can see here, is presenting very high capacity, but because of safety issue, we are using today more graphite than metallic lithium, of course, whose capacity is 10 times lower than the one of lithium. What we are doing is trying to introduce as much as possible silicon, whose capacity is even higher than the one of lithium, but as it under reduction is going to form alloys, it suffers of a very big volume expansion. And so we are diluting silicon in silicon nanoparticles inside carbon matrices. So higher is the amount of silicon, higher will be the capacity, lower will be the amount of silicon, and higher as a consequence the amount of carbon-based particles, the lower will be also the capacity. So the work is now going to increase as much as possible the amount of silicon in the cells. So very briefly, really very briefly, if we consider cathode material, we need to get very high surface. One of the limitation is the low, of course, electronic conductivity. So just to say, if this represents a cathode particle, of course, when we start the reduction mechanism, what is reducing are the outer layer, the first layer of the particle that is in connection with the electrolyte. So the reaction continues trying to reach the core of the particle, but as the material is not a good electron conductor, is an insulator, it is an oxide, the reaction stops. So one way in order to solve this issue is to get nano-sized particles. So if the same amount of active material is present in very small particles, when we have reduction, the active the layer that are reducing are in practice the same as the whole material. Then we need, of course, to increase the electron conductivity. So what we can do is to add carbon, and there are a lot of activities in the field of chemistry, so in synthesing and producing a carbon layer directly on the surface of the particles. So if we have very small particle with a good carbon layer on their surface, and if them are, let me say, inside a carbon matrix, of course, we can assure a good electron movement in the wall cathodic material. So an example is LFP. For example, if you can get a very good carbon layer, as here reported in this nano-sized lithium iron phosphate, you can also reach very high power, as in this case, as an example, this is a laboratory produced material, but you can reach 20 C. And lithium iron phosphate works commercially very well till 10 C with no particular issues. As Daniel already reported before in his lecture about Battery 2030, we have commonly, we are speaking about different generations of materials, of cathode materials. Now we are in generation 3 with the advanced lithium ion materials, so NMC with and the introduction of silicon. We are going to go toward the solid state with the generation 4. And of course, generation 5 is beyond lithium ion, and in particular conversion system based on metallic lithium commonly, but and the post-lithium ion technologies, as Daniel reported, like sodium, potassium, and multivalent system. I already told that lithium is very interesting because of its very high capacity, but during cycling is forming dendrites that can be lost. So we have loss of capacity and also short circuit the whole system. For this reason, I already told about graphite that can be substituted, but we have to remember that during charge and discharge, we have a SEI layer formation, which is a solid electrode interface, electrolyte interface that forms always on the electrode surface. This happens in all the anodic material if they have very low voltage. And this is some capacity lost during first cycle that cannot be recovered during cycling. But the nature of this SEI is very, very important to be studied because it's not so well known, and the use of sensors can also help in this direction. I will cut this just to say that electrolytes are also very important, and they are composed by a lithium salt solved in an organic solvent. Of course, we cannot use all lithium salts because some of them are, for example, explosive. They can be toxic. And again, there's a lot of work needed in order to find the proper salt and the proper combination between organic salts in order to get high safety and the best performance, also adding additives and so on. So as we have many issues related to this electrolyte, liquid electrolyte, because of the need to get an electrolyte that can work properly and not be decomposed depending on the voltage. Higher is the voltage, the better it is because of the energy density, but then the stability of the electrolyte cannot be enough. There are a lot of activities done in order to arrive to all solid state batteries, and then I will be very fast and leave the floor to other discussions. Why solid state? When we speak about solid state, we again are speaking about a very wide range of possible configuration: polymer, gel polymer, ceramic, inorganic ceramic electrolyte, but also mixing of all of them. Why? because in order to, when we are eliminating a liquid electrolyte using solid electrolyte, we can use lithium as anode, so that is will be protected, and this enable the possibility to increase a lot the energy density, but also you have a reduction of the volume of the whole cell. That is very, very important for automotive applications, for example. Okay, we have no time, of course, to go deeper in the work, how solid electrolyte works. It's commonly based on the presence of some electronegative centers that drive the movement of metallic lithium, of lithium ion in the cell. Okay, so really going very fast in the second part. So if you have additional question, of course, I will be very happy to discuss about it. This I will leave here just the link to the Tesla battery days where you have additional information. And so just to summarize, I tried to give a very short and very fast overview about lithium-ion cells reaction, main process in the self-production, cathode, anode, and electrolyte materials, and finally, why and how to go toward the all solid state. Let me really thank, of course, all the funded projects and the European Commission to give us the opportunity to work and get a lot of people, young people engaged and working with us. And in particular, the two projects that are here presented, like SENSIBAT, of course, where we are doing this zeroing course today, and of course, Battery 2030, under which we have the most of our activities. So thank you very much. And forgive me for being a little bit longer. And so now I give the floor to Professor Jürgen Garke, who is a very well known speaker. And thank you for being here and giving us the opportunity to give this course, and particularly of all the work you did in order to assure us this opportunity. Thank you, Professor Garke, and the floor is yours.
Thank you, Sylvia, for the introduction. Best regards from South Germany. I want to give a talk about the battery states from the water innovation in Graz. So the water is well known for their lithium-ion batteries, the micro batteries, coin power, and larger one. And besides the lithium-ion batteries, you have also consumer batteries. That means a primary battery. The water is dealing a long time, you could see, with different systems, starting 130 years ago with the lead acid battery system, and then 1990 the lithium-ion battery system was included, and a little bit later also the lithium polymer system. If you are looking to the different steps of the development from the scientific research up to the product, the water innovation group or the department in Graz is working in that area. So the proven performance of large-scale and full-scale cells are moved then to the larger development to the full production. So the lecture agenda, a short introduction about into the battery state definition, and then the battery states. Different states are related to cycles and to the lifetime. And then the question, which parameter we will use to reflect the different states, the capacity or the energy or the power and so on. And then we are coming to the state of function, that is a relative new parameter, and the state of safety. And then finally, we want to speak about the limitations of the state of charge and the state of health, and what is going on during the reduction of that state parameter. So that means the aging, and finally summary. So the battery states gives you information to the parameter state, and the parameter, for example, could be the capacity of the battery. And we have two groups of states. That is the state of charge during one cycle, that gives you a short time information, and the state of health that is related to the whole cycle life, and that gives you a long time information about the state of the battery. So why we need this information? For example, if you have the screen of your electromobile, then you have here the short time info, the full gauge, the state of charge, and that is the question: how full is still my tank? And then you have the long time info here that give you information about how large is still my tank. So, and that both informations, is short time info, state of charge, and the long time info, state of health, are important for driving the car, and not only for the car, also for other applications. So, and therefore the battery state is a metric to evaluate the current parameter level in relation to its ideal state. So, and the current parameter could be related to a cycle. So that is the cycle state, that is the short time info, or to the lifetime, so lifetime state, long time info. The ideal state could be now related to measured values of a full charged cell, or to a so-called nominal value. And that nominal value is given by the manufacturer. And that is the difference between the ideal state in the cycle, where you measured the value, and for the lifetime value, where the ideal state is given by the manufacturer. So let's have a look to the short time state. So during one cycle, that is the state of charge. That is the ideal value of the fuel cell, full charged cell, 100% state of charge, and then you have the discharge, and then the charge again. So the ideal value is the measured value at that state. So that is the full charge at the beginning of the charge, or at the end of the cycle before. And the current values, that are these values, that are measured values during the discharge and the charge. So the state of charge is the parameter current divided by the parameter ideal. For example, for the capacity, that means the capacity, the current capacity related to the ideal capacity. So, and for the long time state, we have the ideal value, that is the nominal parameter, 100% state of charge given by the manufacturer. And then the measured values of the full charged battery. So if you measure that value, you have to charge the battery up to 100% state of charge during the lifetime. So the state of health is the current parameter, full charged cell, divided by the ideal parameter full charged cell. So capacity related state of health, what the current capacity to the ideal capacity. So let's come back to the nominal capacity. I mentioned that capacity is given by the manufacturer. So that value is based on the experiences of the manufacturer with many cells. So he has a lot of experience, measured a lot of capacities, for example, and the average of that measurement that he calls, the manufacturer calls nominal capacity, or also leveled capacity or given capacity. So that is that value you're looking in the prospectus, and then you see I could buy a cell with 100 ampere hour capacity, for example. But that nominal capacity, that is a given one by the manufacturer, is not in every case the same like the measured capacity. That is the real capacity, which could be in one cell 95 ampere hour, but still is leveled the nominal capacity 100 ampere hour. And the second cell could be have more capacity, for example, 105 ampere hours, but also this cell is still leveled by 100 ampere hour. And in order to avoid problems with the measured capacity, the long time capacity is related in the ideal state to the nominal capacity given by the manufacturer. So again, that both states, the cycle state, for one cycle, you could see that here, the ideal parameter is in the full charged cell, and that is measured. And the state of charge is the value of the parameter during cycling, during discharge and charge, related to the full charged cell. And the lifetime state, the state of health, the ideal parameter, that is the nominal parameter given by the manufacturer. So, and then the question is which parameter we are using to characterize the cell. For example, you have the discharge, and at that point you could measure the capacity, the energy, the power, and the resistance. The same is with the state, with the long time one. You have to charge the cell, and then you could measure here the capacity, or the power, or the energy. So let's have a look to the cycle state. We could have here the measurement of the capacity, the energy, the power, and the resistance. In nearly all cases, for the characterization of that states, let's say 50% state of charge, we use the capacity. And therefore, if we are speaking about the state of charge, that means in nearly all cases the state of capacity. That means the state of charge means practically a state of capacity. So the state of capacity gives you the information about the currently available capacity in relation to the measured capacity of a full charged cell. That means that point. The capacity reduction, so that means that one up to that one is largely reversible. So you have not big changes between that capacity and that capacity, practically no changes in one cycle. The state of charge units are percentage points. So 0%, that means empty, full discharge, 100%. So the state of charge is a kind of fuel gauge, and the answer on the question is how full is still the tank. And here you could see the relation of the state of charge in relation to the capacity that is linear. Okay. If we are looking to the other possible cycle states, the state of energy or the state of power, an analogy to state of charge is also related to the values of the full charged cell. But in opposite to the state of capacity, the state of energy and the state of power is the integral between the voltage and charge and the voltage and the current. But the voltage during charge and discharge is not linear. So you could see here the open circuit voltage for NMC value, and therefore the changes in the state of energy and state of power versus state of charge are nonlinear as well. So the lifetime state, that means that is the state of health, and that is the value to evaluate the health, let's say the aging in relation to its ideal state. So like the human, we have a different explanation for the health. You could look to the skeleton, to the blood power, the nerves, and so on. And the same we have here for the cell. We have different indications. Oh, sorry. Oh, moment. We have different indications for the health. That could be the capacity, via the lifetime, the energy, and the power and the resistance. So it's the same like the cycle state. We have here the capacity related to the to lifetime, the energy, and so on. And also here we are using as a parameter to characterize the state of health, the capacity. So also here in the lifetime state, the state of health is practically mostly the state of capacity. So if we are looking now to the state of health related to the capacity, we have, for example, 100% state of health. That is a new battery that is here, and the capacity is given by the manufacturer. And then you have a value at about 80%. That is the end of life per definition. The real end of the chemical life is at 0% state of charge. But normally in the electromobility, the end of life is related to about 80% of the nominal capacity at the beginning. The capacity reduction, of course, is largely irreversible. And the state of charge is, the state of health, sorry, is a lifetime indicator. And that gives the answer, or the question is how large is still the tank? So green, that would be 100%, and red, that would be 80%. So, of course, we could have also here the other states of energy, of power, and also the state of resistance. And sometimes it's also used the state of resistance because not for all, but for the layered materials like NMC and NCA, we have a relation of the capacity to the resistivity, to one divided by the resistivity. So, and then is introduced a so-called state of function. State of function. That state of function combines the state of charge. So that means the capacity during the cycling and the state of health. And that state of function, that is the answer to how big is still my fuel tank and how full is still the fuel tank. With other words, how many kilometers I can drive with my car. So the state of function is not differentiated between the capacity decreasing during one cycle and the capacity decreasing related to the aging. So that is the other state function, the so-called state of function. So, and then it's introduced also a so-called state of safety. And we have a lot of safety risk. I will give later a lecture about the safety, and you could see we have the electrical, chemical, thermal, and so on risk. And the problem for that state of safety is the quantification of the state of safety. State of safety is used in the literature often, but never defined exactly. And there are operation parameter limits which are not to exceed it. For example, that is the operation window for the temperature or for the charge rate, and you should not coming via that or the outside of that operation window. And based on that limits, so the temperature, the charge rate, a function could be developed for that state of safety. There's a good publication in the Journal of Power Sources. So, are there any limiting values for state of charge and state of health? Yes. For the state of charge, so normally you should, that depends on the battery, on the chemical battery system. You should not go deeper in the discharge in relation, to about 20%. The end of discharge would be here 80%. So why we are doing that? To stop here the discharge, to increase the lifetime. If you are going deeper to about 100% discharge, then the lifetime is decreasing exponentially. And then you have sometimes also an end of charge limit, for example, at 80% state of charge, and especially in hybrid electric vehicle. The hybrid electric vehicles they are using to charge the battery, for example, the regenerative braking energy. And if your battery is already full, 100% charged, then you have no chance to absorb the braking energy. Therefore, you have an upper limit, it's about 80%. To enable the charging, and you have also a lower limit, it's about 20% state of charge. And for the state of health, you have also limiting values. You could see that here, 100% state of charge you will have in your car, the green line, then the yellow line at about 85%. That means please drive in a workshop, in a car workshop, and then the end of life per definition. For the cars, 80%. For other application, for example, for stationary application, also deeper. Oh, and then the last question, reasons for battery state reductions. In the state of charge, normally the reduction of the capacity, via one cycle, if you are going from that point to that point, that is very low. So the changes during one cycle are nearly reversible. That is not the case in the state of health. The reduction via the lifetime, they are relatively higher in relation to the state of charge. So the reason for the state of health reductions are the loss of lithium, that active, furthermore active mass losses and move charge inability. So about that reasons I will speak in about 30 minutes. The summary, we have the cycle states, short time, mainly state of capacity that give you the relation between the measurement parameter in the partial charged state, lower than 100%, in relation to the ideal state is the measurement parameter of the full charged battery. So, and the question was how full is the tank? And then you have the lifetime state that is also related mainly to the state of capacity. And that is the current parameter, the current capacity of the full charged battery to the ideal state. So, and then we have the combination of the state of capacity and the state of charge and the state of health as the state of function, which gives you the kilometer which you could drive, and finally also a state of safety. Yeah, thank you for your attention, and please see in September we have in Graz the 4th Graz Battery Days, tools to tackle the challenges of lithium-ion battery technology, mostly related to sensor topics. Yeah, thank you very much.
Thank
Thank
you
you.
very much, Jürgen.
Sylvia, you are on mute.
Now it looked to be. Can you hear me now?
Yes, it's working
Okay,
again.
because it wasn't delayed. So forgive me. We will we have a short coffee break now, and so we will meet here again at 10:45. And I was just saying that if you have any question, please write them in the chat. I will take note, and I will ask to speakers to answer later. So thank you very much. Take your coffee. In 15 minutes, we'll be here. Thank you very much. And thank you, Jürgen, because I was also thanking you before. See you in a while. Okay, so we are almost ready to start again. So I took note of your questions. So we will have time after the next presentation to answer. So in a while, we are going to have a new presentation on the processes influencing lifetime states. I'm proud to say that we are more than 180. So now we are something like 186. So it's a very good and hope that it's also interesting for you. So now somebody else is joining. So maybe we arrive to 200. So I don't know if Jürgen, you are here and you want to start sharing. I cannot see him.
Yes, no.
Thank you. Thank you. Sorry.
Oh,
Great.
so,
Hope you got a good coffee.
yeah.
Thank you.
Etching capacity.
Great. It works. Thank you.
Could you see that?
Yes, we can see it
Okay.
well. Thank you.
Okay. Should I start?
Yes, of course.
Okay. Okay.
Thank you.
Well, hello, everyone. This lecture is giving an overview about the influence of aging on the capacity. Yeah, the water I have introduced already, and the agenda is now shortly the battery state definition again, then reversible and irreversible changes, and then the reason for the irreversible changes, lithium trapping and active mass losses. And then finally, the influence of the temperature on aging. So that we discussed already in the lecture before, the state of charge during one cycle and the state of health during the whole cycle life. And the state of charge during one cycle, practically, we have only reversible changes, practically only reversible changes, and the state of health, the changes are reversible. So I mentioned practically, you have no changes in the capacity during one cycle from Cx to Cx plus 1. Of course, you have minimal changes, but practically you could not see the changes during one cycle. So the other lifetime or the other state of charge, the state of health, all that changes during the lifetime or the cycle numbers are irreversible. So, and we have 3 groups for that, and I will discuss only the loss of lithium and active mass losses, and not the move of charge and ability. We could do that in the discussion, for example. So the reason for capacity fade and power fade is the loss of lithium in the system. And we have two reasons for that, two mechanisms for that. That is the lithium formation and the lithium plating. And now I will address the lithium formation. Starting to understand what is going on with the electrolyte stability, with the well-known example of water. You have two platinum electrodes, and if you are going to the lower potential at about 0 volt, hydrogen is involved, is generated. So in that region, the water is unstable and going in the positive direction at about 1.23 volts. The water is oxidized to oxygen. So only in that region we have the electrolyte stability window. That is for water, but we could take the same model or the same experiment also for our lithium electrolyte, the LiPF6 alkyl carbonate, and we have here two gold electrodes. And we have nearly the same behavior. We are going in the positive direction, and then the electrolyte is oxidized, and we are going, and if we are going in the negative direction, the electrolyte is reduced. So that area here we had 1.23 volts, and here we have nearly 4 volt electrolyte stability window. So that means we have two areas for the stability. That is the electrochemical window between 1 volt and 4.5, 4.3, 4.6, depends on the electrolyte. In the alkyl carbonate, and outside that windows, for example, anodes with the potential lower 1 volt are not stable, and also cathodes with the potential higher than 4.5 volts are not stable. So if we are looking now in our material window or on material picture, here we have the electrochemical window shown here, and outside we have only some cathode material. In the moment, not so important, but in the anode area, lower than 1 volt, we have the graphite and also the lithium. So that means if we have active masses with a potential higher than 4.5 volt, the active masses will be reduced and the electrolyte will be oxidized. So that is what we have seen here. And in that case, the electrolyte is reduced and the active mass is oxidized. So that is in general. And you could see that here. Again, that electrochemical stability window, and the lithium nickel mangan oxide is outside, and also the nickel mangan oxide different composition is coming up at about, let's say, 50% charge. We are coming also in the instability area. And the graphite charge curve you could see here, we are below that 1 volt. That's good because the potential is high, or the potential is important for the graphite. And here also we have the lithium in that area. One anode material is outside, or inside better, of the electrochemical window. That is the lithium titanate. You could see that here. So what is going on if you are outside of that electrochemical window? The graphite, the lithium-nated graphite, is reacting with the electrolyte. And that is a chemical, only a chemical, not an electrochemical reaction of the graphite with the electrolyte. And there are solids are formed, lithium carbonate, that one, and also gases are formed during the chemical reaction between the graphite and the electrolyte. And that chemical reaction built up a so-called solid electrolyte interface, solid electrolyte interface. The good one is that SEI is conductive for lithium ions. So the lithium ions could go through that layer. So the good one from one side is the SEI is avoiding the graphite exfoliation, the cracking of the graphite. So normally, without the SEI, the lithium ion is going into the layers between the graphene layers, solvated. So you could see that here. And that solvated lithium ion is much larger. And so the graphene layers will be exfoliated. And if you have the SEI, then that's very good. You have no more exfoliation, and the lithium ion is not going in the solvated state, so it's going only as the lithium ion in the graphite. But the thickness of that SEI is growing via the time. In the beginning, very fast, and then slowly, but constantly slowly. The growth rate of that SEI depends on the temperature, the state of charge, and also on the electrolyte composition. So by trapping of lithium in the SEI, you could see lithium fluoride, lithium oxide, lithium carbonate. That lithium is trapped. That is no more free to transport from the anode to the cathode and vice versa. And that means that bring you a capacity reduction. And the increase of the thickness of the SEI leads to an increase of the resistivity of the whole system. And that means you have also a power reduction by the SEI. So let's have a look to that mechanism. We have layered materials on NMC, for example, that are the metal oxide layers. In between, we have the lithium. So, and here we have a view on all lithium in the cathode. And we divide that all lithium in one part that is structure stabilizing the cathode material. If we have no lithium between that layers, no lithium, all lithium is outside, then the structure is collapsed. So the layers are going together. The layers are going together. So we need a part of the lithium as the so-called structure stabilizing. And the other part, that is the capacity forming. So, and now we have the assembly. We have the cathode with the structure stabilizing and capacity forming. And in the assembly, we have the empty graphite. So, and now we are putting the electrolyte in the cell and charging the cell, and then the capacity forming lithium is going in the anode, but not the whole capacity forming lithium, only a part. Another part, the smaller part, is forming the SEI. And that formed SEI, that is the irreversible capacity loss. And if you are looking in the first charge, so that is the empty graphite electrode. You charge it, you coming down, and then you are going back with the to discharge that one. You have here the so-called irreversible capacity loss. And that irreversible capacity loss, that is formed SEI during the formation. But during the lifetime, because that is a chemical reaction, and I mentioned that layer is growing independent on charge-discharge, and so we get a larger and larger SEI, and that means in parallel a capacity reduction. And Harald Krehn von Water Innovation measured in his dissertation the mass of the SEI in the cathode, and then he calculated via that mass of the SEI theoretical capacity loss. And that is the result of the calculated capacity loss. And then he measured that. And you could see that here for the 0.1 discharge, the curve is nearly the same like the calculated one, because your SEI is grown. For 5C discharge, we have deviations, that's clear, because with the higher current, we have a lower discharge voltage, and therefore the capacity is also reduced. So, and then you have temperature influence on the growing of the SEI. You could measure that without any cycling. You put only the graphite electrode, the formated graphite electrode in thermostat, and then you measure the capacity loss, 10, 20, and so on. And here you could see after 400 days, you have a good Arrhenius dependency. So that means the reaction rate of lithium-nated graphite and electrolyte is increasing with the temperature as expected. And then you have also a state of charge influence. If you are looking to the discharge charge curve of the graphite electrode, here you have the stability limit, okay, and that is the potential of the graphite electrode in state of charge 80%. And that is the potential of the state of the graphite electrode as a state of charge 20%. So here you have a higher potential difference at 80% to the stability window as in case of 20%. So that potential is lower. And therefore, the reaction rate at the graphite electrode with a state of charge 80 or 100% is larger than the reaction rate of the graphite electrode with 20%. And you could see that here, that the graphite electrode with 100% state of charge is aging much faster than in relation to 10%. And then we have also a third influence besides the temperature and the state of charge. That is the manganese deposition into the SEI. So normally that is the cathode. You have the manganese 3, for example, in the NMC, and especially in case if you have HF developed from the conductive salt, you have a disproportionation. You have a general disproportionation, but in presence of HF, the disproportionation is going much faster. And the disproportionation is going in mangan 4 plus, that is solid, and in mangan 2 plus, which is liquid. And that liquid mangan 2 is going then to the anode, and at the anode is reduced to manganese elementary. And then you have manganese clusters in the SEI, and so the SEI is no more stable as in case without the clusters. The second mechanism for the loss of lithium is the lithium plating. If you are looking to that discharge charge curve of graphite, that is intercalation, you are always, if you have a normal discharge charge current with a potential higher than the lithium potential. So you have no plating or lithium deposition as long your anode potential is higher than the potential of the lithium electrode. But you know, via that equation, if you have a high current, then your charge potential is decreasing, like in that case. Here we have a normal charge current, and here we have a strong charge current. So the curve is going that way. And here, let's say at about, in that case, 50% state of charge, we are crossing the lithium potential. And if you are lower than the lithium potential, that means here you have lithium metal depositions. And the lithium metal depositions we call lithium plating. So at high current we have lithium metal plating here, and normal current, so we have the intercalation into the graphite. And that curve, the level of that curve to the lithium electrode depends on the current, that's mentioned, also on the temperature, and also on the state of charge. So what is lithium plating doing? Normally, the plated lithium after some rest could be discharged as well, but repeated lithium plating is forming cracks in your SEI, and then your SEI is expanded, and then small lithium dendrites are forming. And these small lithium dendrites could be isolated if that connection to the basic material is disappeared. And then you have isolated lithium, and we call that isolated lithium because it's not connected anymore to the basic electrode. We call that dead lithium. So that lithium is no more contribute to the capacity. So here you have some examples from real cells, and you could see that by the color that the anode, that is the normal one, the graphite, and that is a lithium plated one. So the condition for platings, we mentioned that high temperature and high current and low temperature, because at low temperature the resistivity is increased and then also that curve is decreased. So, and the temperature influence, that is really a problem for the fast charge. On the left side, you have the increased current, or that is the charging time to 80% state of charge in minutes. So 10 minutes, that is a very high charge current. And here you have a line. On that side, you will find lithium plating. And on the other side of that curve, that is lithium plating free. So, for example, if you want to charge your battery in 30 minutes, it's about 2C, you need at least to charge your battery at 40%, 40 centigrade. So if you want to have 20-minute charge, okay, your charging temperature should be 50 centigrade. And that is exactly what Tesla, for example, is doing to avoid lithium plating. Just before you charge the battery, fast charge your battery, your software is heating up your battery to about 40 centigrade, and then you could charge that with the high charging current. So, and that lithium, which we have seen, that is also trapped lithium, and that reduced your capacity. So now let's come to the active mass losses. The active mass losses are coming normally via the contact resistance increase. So you have a mechanical stress inside, and that mechanical stress then reduce your contact between the particles. And not only the contact between the particles, but also between the particles and the collector. If you are looking, for example, to the mechanical stress, that is the graphite electrode. Here is the SEI, and now the lithium intercalation is going on. And you could see here, like the volume stress is going into the graphite via the charging time. And that stress in the graphite, that will be have also a feedback to the SEI, because that stress that cracks the SEI, and then the electrolyte could react much faster with the graphite. And also that mechanical problems are well known with the lithium silicon alloys. Silva has mentioned that they have a high volume in case of charge and discharge. That is the volume for the charged one, and that is for the black one, that is for the discharged one, and that for the charged one. For the graphite, it's the difference only 10%, but look for that alloys, the difference is about 40%. So, and after some cycles, so you have an electrochemical melting. So you have no more contact. So that is active mass loss. That is an example, an example for the lithiination of a silicon. What you see here is a silicon. Oh, I hope I could come back. Yeah, you could see the lithiination of the silicon. The increase of the volume and that will bring you a higher volume and mechanical problems. And besides that, mechanical problems, which leads to contact losses, capacity loss, you have also chemical problems because you create a new surface, which is not collected with the SEI. And so you have to form after the charge of the silicon a new SEI, and the new SEI, that means again capacity loss. So let's have a look on the volume changes during cycling of conventional batteries, the LFP battery. You have in the LFP a volume change during charge and discharge of about -6-7%. And on the graphite electrode, you have a volume change by +6-7%. So you have practically no volume change. So you have low pressure on the separator, and that is a very stable structure in the LFP, and you have longer cycle life in that case with LFP batteries. In the case of the layered material, for example, NCO, for the graphite, 6-7%, for the LCO plus 4, and that is added to about 10% volume change, and then you have high pressure on the separator and stressed structures. So, and if you are looking, for example, to the lifetime of LFP cells and layered material cells, you could see the advantage of the LFP, which compensates all that volume changes from the anode and the cathode, and that is not the case for the layered material. So, and then a short introduction in the layered material in the charge and discharge. The discharge material has a lot of lithium between the layers, and if you charge that one, then you de-intercalate the lithium from that structures. So you have lower lithium ion concentration. And as we are expected, if you take out delithiumated more than in that case, the structure could be collapsed. But you could try it. And if you go to higher charge potentials, you could see that here, also your capacity is increasing. But the end of charge, 100% state of charge, is given by definition, not by physics or chemistry. Because if you are going to that higher values or higher de-intercalation, your structure is no more stable, and the lifetime is decreased. Therefore, all experts give us the upper charge voltage for 2.5 or maybe 4.3. If you are going to higher values, then what you are doing, you are using a part of the structure stabilizing lithium as capacity forming lithium. You get a higher capacity, but a lower, as you could see that here, a lower lifetime, because the structure is starting to collapse if too much lithium is de-intercalated. So, and now a short information to the temperature influence. The lithium trapping, so mostly the SEI formation, is increasing. We have seen that with increasing temperature. And what you see that here, that is the logarithm of the aging rate. So, and by our knowledge of the Arrhenius one, we could expect it that the aging rate will be decreased if we are going to lower temperatures. So that is the expectation. But we know now the SEI formation, that's right, it's going that way. But the lithium plating, we know that at low temperature, we have a very high lithium plating is going in the other direction. So we have altogether for the influence of the temperature on the aging rate a minimum. And that minimum is formed by the SEI, thickness growth, and the other side by the lithium plating. And so we have to take in our mind that we have optimal temperature range where we have the maximum cycling life. If you go to deep temperatures, the cycle life is going down, and also to higher temperatures. So, and here you have a lot of combination of the time, the high temperature, in the different degradation mechanism. You could read that here. I don't want to go too deep in that mechanism, but we have the 3 degradation modes: the loss of lithium, the loss of active material, and capacity loss and power fade. For the summary, we have the loss of lithium by SEI formation outside of the stability windows of the electrolyte. And we have the lithium plating if we are coming with our charge potential lower than the lithium electrode potential. And that leads to that lithium plating leads to dead lithium and reduced capacity. And active mass losses, we have the mechanical stresses, 2 different systems, what you could see that here, and systems with low stress like the LFP has a longer lifetime in relation to systems with higher stress, and that are the layered material like NMC and NCA. So, and the summary of the temperature influence, you could see that here, not as we have expected. Low temperature could be very good for the aging. No, this is not the case caused by lithium plating. So again, thank you very much for your attention, and then also see the Graz battery days in September. Okay, so and then I will go to the next one. Aging and fans. Yeah, that is the right one. Could you see the aging on safety here?
Yes, well,
Okay.
thank you.
Okay. So I'm starting now with the influence of aging on the safety of the battery. Again, the water. And I have divided the lecture in 2 parts. In the first part, I will introduce you in the probably not well-known problem of safety. And in the second part, I will address the influence of aging on the safety. So starting with the introduction chapter on safety, aging, and then coming the aging influence on safety. Here we have an example. Don't never do. No. So again, do not repeat that experiment. What we learned, obviously, lithium-ion batteries are dangerous if you are doing that experiment, of course. So I learned that in one of the conferences, the one leading person asked, is the lithium battery a controlled bomb? And if you look to the energy density of the TNT, this, that one, and the energy density of a lithium-ion battery, not too high, specific watt-hour per kilogram. So we are in the same region like the TNT. But don't worry, the chocolate has much more energy than the lithium-ion battery and the TNT. So you notice high energy densities do not pose an inherent explosion risk. So in general, we have to say lithium-ion batteries are dangerous, but only outside of the working window, the operating window. I mentioned that already. You have the standard operation windows given by the voltage, current, temperature, state of charge, and that is relatively good control. And then you have environmental data, water, mechanical forces, high temperatures. They are bad control. So mechanical forces like accidents and so on. So here we have such operational design failure. So, okay. But that was an operational failure. The car was running in the parking slot and started to explode. And then we have the mechanical impacts, the road incidences. We know that from Tesla, and not only Tesla, also other incidences. But the question is, what about the internal combustion engine cars, the gasoline, diesel, and so on? In the States, every 2 minutes there's a car fire. So, but in Germany we have about 70 internal combustion engine cars per day. 40% is the electrical installation, 40% is related to the engine, and 20% in Germany is vandalism. Maybe in France is a little bit more, but about that 70 internal combustion engine car fires, you could not read every day about that in the newspaper. But if one electric car is burning, then you could read that. So the general, I have to say, the lithium-ion cells are safe as long you are working in that operational window. The incident rate is lower than 0.1 ppm. What are the main safety problems? You have seen that already. You have the electrical problems. Electric vehicle cars now have 800-volt batteries, for example. Then you have a kinetic, so the explosion one. You could see this here with the NASA robot. The exploded overnight, as you could see here. And that question we have discussed, the explosion risk of the battery and the TNT is nearly the same, but the energy density of the chocolate is much higher. The question is why? There is a so-called Berthelot-Roach's product, which gives you information about the explosion risk. And that Berthelot-Roach product is proportionally to the gas products, to the volume of the gas products, which are developed during that accident, multiplied by the reaction enthalpy. And here we have different examples. Lithium with the inorganic electrolyte, lithium cobalt oxide, and 5, that is black powder. And here we have the explosion limit. And we have I will address 2 examples. We have the lithium organic electrolyte, LMO, with that very high product, and the lithium inorganic electrolyte. That inorganic electrolyte is the ionic liquid with lithium tetrachloroaluminate, and the SO2 ionic liquid is produced in a demonstration by Inulit in Germany. And you could see the inorganic electrolyte that is not developed so much gas volume like the organic electrolytes, the polycarbonates. Therefore, the explosion risk of that organic electrolyte is much higher than the explosion risk of nearly the same cell with the inorganic electrolyte. And the explosion risk caused by low gas volume is the chocolate that would be here, because the volume of gases are very low in the reaction phase. So the third hazard is the chemical hazard, which is related to toxic gases, toxic substances on the health and environment. So the main risk, the main chemical risk, is coming from the electrolyte. And we have 3 cases. We have a cold leakage, that would be a leak at low temperatures. What we could see here, we have HF formation. And then we have high temperatures, but no fire. So we have gas development and the cell pressure, flammable gases, toxic gases. The vent opens, controlled. So, and then we have the case C, that is fire. The container is opened mostly uncontrolled, and gases ignite. And toxic, the CO, HF, and that is the hazard gases. So that would be an example for that one. The pressure is increased in the overcharge, and you could see that here. And finally, after the fire, you have the explosion. So the question to the toxic part of the gases in after the explosion, you could see here 3 different chemical systems. The CO concentration for the LFP is about 5%, NMC about 13%, and here NMC and LCO nearly 28% CO. So you have an increase of the concentration, of the gases. And we have nearly the same electrolyte. And therefore the question is why we have that increase in the carbon monoxide concentration. If you are looking to the heat release rate via the time, we have two groups. You have the high energy material, the NMC and the LCO. You have an early start of the heat release and with a very high maximum. And then you have the low energy materials like LFP coming later, and the heat release rate is not too high. So in case of the high energy materials like NMC and so on, you have a fast combustion. And fast combustion, that means incomplete combustion. And incomplete combustion, that means you have a high carbon monoxide concentration. And in the low energy materials, you have a slow combustion, complete combustion, and a low CO concentration, what you could see that in that case. And the high chemical risk is related to the conducting salt. You have the decomposition of the LFP. You could see that here up to the HF. And HF, that is a strong toxic material. And finally, the main safety problems, we have the thermal risk. And the first question is, what contributes to that high lithium ion cell energy? If you are looking to two parts, we have that is the older 18650 LCO cell. You have the electrical energy, and you have the chemical or thermal energy. So that had nothing to do with electrical energy. At temperature at about 120 centigrade, the anode or the SEI reacts with the electrolyte, and at about larger than 180 centigrade, the cathode reacts with the electrolyte, and at about 450 centigrade, the electrolyte combusted. So that are the two parts of the energy. So the electrical energy could be will be converted in case of short circuit in heat as well. And if you are looking to specific heat capacity and specific energy, you have a relation of about 720 Kelvin. So that means 1% state of charge loss in the short circuit increases cell temperature by 7.2 K. And if all electric material or electric energy is reacted, then you have a cell temperature increase by 720 K. That is under adiabatic conditions. That is not real practically because you have also temperature actions. But that short circuit reaction of the electrical energy that's heated up your cell, that acts like a lighter. So, and the energy which is created by that lighter, that heated up the cell temperature, and then the reactions, the chemical reactions are triggered at temperature at 120 centigrade. So now you could say, okay, let's discharge our cell. Then we have no lighter to trigger the chemical energy. That's right, as long as there is no outside thermal trigger. And that is not in every case the case. So thermal trigger to come to higher temperatures. Mentioned that you have the internal short circuit and the external short circuit, where the electrical energy is converted in thermal energy. Then you have operating parameters, which outside of the operating window, overcharge, deep discharge, over external heating, and so on. That means you have a temperature increase. And then you could come to that anode SEI reaction, thermal decomposition, burning of the electrolyte. So let's look theoretically. We have a thermal input. Physically, the temperature is increasing at about 100 centigrade. The vent is open by the boiling point of EMC. And then if the temperature is increasing further to about 120 centigrade, the anode SEI react with the electrolyte. That is the exothermal chemical reaction, about 300 kilojoule per kilogram cell. So at temperature lower than 120 centigrade, you have here the original SEI. And if you are coming to temperatures of about 120 centigrade, organic SEI compounds, you could see that here, the organic metastable compounds are solved. So the primary SEI, that one is decomposed. And then you have again the possibility that the electrolyte reacts with the lithium graphite. And then the secondary SEI is formed only with inorganic components and also in the exothermic reaction. So that means caused by that reaction, the cell temperature is increased. And coming to about 180 centigrade, that is the decomposition of the layered material. So the LCO, for example, or the NMC is decomposed to lower oxide values and to free oxygen. So free oxygen, that means that it's like gasoline in a fire. And that free oxygen, that reacts immediately with the electrolyte and also with the graphite. So that oxygen reacts also with the electrolyte and graphite. So you will see in that temperature diagram via the time T1, that is the SEI decomposition. Here is the decomposition of the cathode material, and then here reacts the electrolyte with the oxygen with the electrolyte and the graphite, and you're coming to a very high temperature, and we call that thermal runaway. But the thermal decomposition temperature, that means that T2 depends on the chemistry. We have here arc measurement, so the heat rate is measured via the temperature. What you could see, the LCO started, that is the T2, at 180 NCA, 220 NCM11, 240 LMO, about 280 LFP, 450 centigrade. So that means these materials are more stable or temperature stable, like the layer material like NMC and NCA. What is the reason for that? What you could see here, that is the oxygen binding, the bonding energy. For nickel, it's relatively low. Cobalt, it's here. And manganese is much better, and aluminium as well. So if you are looking to NMC, you get with nickel a high capacity but a low safety. And you know the development of the NMC. We are coming from the 3.3 or 1.1 to the 8.1.1. It's a higher capacity. It's very good. But the thermal stability is decreased as well. So we have higher capacity but lower stability. And what the developer are doing, they are working with layers on the nickel material. So, and if the temperature is increasing, we are coming to the electrolyte combustion with a very high enthalpy value. We can repeat that or have the cell here. We have done that. Burning with the Bunsen burner. Here the vent is open, and now we are coming to the decomposition of the cathode material. At that point, the cathode material was decomposed, the oxygen was generated and reacts with the electrolyte and with the cathode. So, and you could see that again here. That is the SEI electrolyte reaction, cathode decomposition, and here the electrolyte combustion leading to a thermal runaway. You could measure that with the arc, with the accelerated arc currently. The box is heated from the outside heaters, and here you have your cell, even a battery if you have a larger arc, and the sample has a temperature sensor, and then you're heating up the outside or the box temperature, no reaction, going to a higher temperature step by step, no reaction. And here you measured the increase on the temperature of the cell, and then you get the information at that temperature. We have a chemical reaction inside the cell. The self-heating rate is increased. So that is the so-called thermal runaway. Then, if you come to the burning of the electrolyte, thermal runaway, we will observe if the generated heat in the cell, generated by combustion and cathode decomposition, is higher than the cooling rate. Cooling rate is stable here, and here we have that relation. That means the heat generation is larger than the cooling rate. So, and that leads us in the thermal runaway. What we could do, we could, to avoid the thermal runaway, we could use non-flammable electrolytes. That means to decrease that area. And otherwise, we could increase our cooling heat by cooling the systems by air, by liquid. And we could also look for larger cooling areas. If you have a small cell, the volume of the cell, so the active mass, determined the Q generation, and the area of the cell that determined the cooling rate. And in the case of the 2 ampere hours, we have the volume to the surface is 1:1. For larger cells, so 40 ampere cells, the volume is about 20, and the surface is only 7. So the cooling area is reduced by a factor of 3. for a 40 ampere hour cell in relation to a 2 ampere hour cell. So to prove of the state of safety, we are doing safety test. A safety test, you have the excitation of the cell, mechanically, electrically, thermal, crash, short circuit, thermal stability test. And there's a lot of different excitations and therefore a lot of different testing conditions. You could see that here, external short circuit, abnormal charge, force discharge, crash, impact, and so on. And you have different standards, and you could see external short circuit, all standards use that external short circuit. And another one is the crash, also all one. And there is a so-called, I'm looking at here, penetration. That is a nail penetration test. Not all standards are using that, and I will shortly explain why. You are looking after the excitation to answer. Voltage current is gas, toxicity, volume pressure, mass loss, and fire explosions. That are answers. And the Sandia lab, the National Sandia lab, has developed such a hazard level figure, which is used also by UCAR. And you have the different test results which are related to hazard levels. For example, electrolyte loss, lower than 50%, that is hazard level 3. Electrolyte loss, much more than 50% or more than 50%, 4. Venting, 4, and so on. And fire and flame, 5, 6, and explosion, 7. And up to here, hazard level 4, all tests are passed. If you have a hazard level of 5, then the test is failed. So that is the summary of the introduction. Now you have causes, the external short circuit, internal short circuit, overcharge that heated up the temperature of your, or bringing up the temperature of your cell. And then you have two possibilities. Your cooling is larger than the generation heat, then you have a safe outcome. But in most cases, your generated heat is higher than the cooling rate, and then you are coming in the thermal runaway, venting, rupture, fire, and explosion. And now we are coming to the aging influence on the safety. So the aging brings the aging also a safety problem is the question. I have to tell you in the beginning already, for the time being, we have no clear pictures in the literature. You have literature, the green one is writing after the aging, the cell will be safer, and you have the red one, the aging bringing you more risk. You could, I could bring you much more literature examples which show you green lines and also red lines. So that is not really clear how aging influences safety. If you are looking, for example, the aged cells, you have a capacity and energy loss. You know that, yeah, of course. And the result is a lower electrical energy. So from the safety point of view, capacity loss, aging, that should bring a safer state of the battery. You could see that here, for example, that is the state of health or state of charge. If you have 100% state of health, you have a lot of cathode material which could be decomposed, and then the reaction is started. If you have a low state of health or a low state of charge, so your heat generation is reduced. And you could see that here, that is the maximum temperature, maximum determined runaway temperature. It depends on the state of charge and also of the state of health. If the battery, the cell is discharged, you could see the maximum temperature is 300 centigrade, and in full charge you have 900 centigrade. So the second one is the SEI formation during the aging of the cell. That brings you a higher thermal energy. And the higher thermal energy, that means more risk. If you are looking to the heat flow, to the arc-1 measurement, you see a higher temperature development of the SEI after 200 cycles in relation to 10 cycles. So that means you have a stronger temperature increase after 200 cycles related to the case of 10 cycles. So then the lithium plating, you have metallic lithium, that is a higher thermal energy, that is more risk. And then you have the formation of that lithium, that is a lower electrical energy. So that means your system should be safer. Here we have an example measurement at the ZSW in Ulm, caused by lithium plating. You could see only the reflection of the deep temperature on the state of health. So that means on the capacity decrease. If you have a cycling at minus 10 centigrade with 1C, you could see a strong decrease in the capacity. So on the maximum, you could reach, let's say, 20, 30 cycles. And if you are doing the cycling at 25 centigrade and at 16C, that is a tremendous current, you have a much larger capacity as in case of the deep temperature one. So, and here you have the results of the arc measurement with the fresh, with the new one, the new NMC, which were cycled at minus 10 centigrade, and they are going in the thermal runaway. So normally we say thermal runaway started if we have 10 centigrade or 10 Kelvin per minute changed at about 220, and the aged cell cycling at minus 10 centigrade, the thermal runaway started at about 120. And that show you the aged cell after the arc measurement. So this exploded. So normally in that case, you could see that here from the colleagues from Münster, the self-heating rate for a fresh cell is here, and for the aged cell, aged at 70 state of charge and no centigrade is here. So, and then we have the dendrites, the short circuit, that bring you more risk. We have discussed the possibility of manganese shorts. You could see that here the manganese dendrites could go to the cathode, and also lithium could go to the cathode, and also copper could go to the cathode. So we have the inhomogeneous deposition caused by inhomogeneous SEI. We have the glow of the dendrites, and the dendrites could go up to the cathode. So that is the example, a demonstration how the lithium dendrites are growing. You could see that here in the mossing structure very fast. So not every dendrite gives you a real short circuit which is heating up your cell. That depends on the length of the cell and also on the diameter of the cell. So if the dendrite resistivity, that is depends on the diameter, the cell is the dendrite diameter will be larger, then the resistivity is decreasing, and with decreasing resistivity, the short circuit current is increasing. So, and we have here, for example, two cases. The diameter of the dendrite 0.1 micrometer, and here 1 micrometer. And here we will have a thermal runaway, and here we will have no thermal runaway. The voltage, if you have a short circuit, so normally the voltage is going down. And here we have a case, an example, not in every case we will find that. Here the dendrite is burned down. So that means the dendrite is coming to the cathode, the voltage is going down, the temperature is increasing, and the temperature will be so large that the dendrite peak will be interrupted. So you have no more short circuit. Otherwise, if you have a continuous contact of the dendrite with the cathode, then the voltage is going down and the temperature is increasing. You're coming to the thermal runaway. So again, that results, and we have now different influence on the aging reaction, or different influences of the operating parameters on the aging reaction. So capacity energy loss depends on the time, on the cycling condition, on the open circuit voltage. It's the same is in the formation. The plating of the lithium depends on the state of charge. We have shown that on the temperature and the current. And lithium dendrites depends on the cycling behavior, on the current and potential. And because that operating parameters are changed, or they could be changed from case to case, then also the aging reactions are changed. So, and therefore you need to know the aging history. So what was going on in the first 100 cycles, at which temperature, with which current, charge and discharge, and so on. And then you could nearly say which of the parameters take influence on your safety. So if the charge rate is increased, then the capacity is going down, the upper voltage limit is going down, lower voltage limit is going up. So you have really to analyze all that operating conditions. That gives you an overview about the temperature and the voltage limit. For example, here, the low voltage and the high voltage limit and the temperature, and you have normal area, relatively safe area, damaged areas. Oh yeah, that we have. So summary, the main safety problems are electrical, kinetic, chemical, and mostly the thermal. The cell energy content, the chemical to the electrical, is about 3 to 1, and the chemical energy must be thermally triggered and will be thermally triggered by a short circuit of the electrical energy. The aging influence on safety, that is capacity, energy loss, SEI formation, plating, and dead lithium and dendrites. And that depends on the aging reaction, which are influenced by different operating parameters. So caused by that relation, the aging relation to the operating parameter, so we could find improved and also reduced safety states. The standard operating windows has to adapt with the age, and that is a little bit a problem. Yeah, we wrote together with Klaus Brandt a book about lithium batteries 4 years ago. And again, thank you for your attention, and maybe we could see you in September in Graz. So yeah, that's all from my side now.
Thank you very much for these very clear and exhaustive presentations. I think you covered a lot of the issues related to safety and the battery states. There are some questions I can give you. I can try to read some of them. I will start from those more related to the battery states, and then there are also some few questions about solid state and so on. That is more, let me say, less focus on the topic here treated. So one of the first question I just copied in a file, so sorry. Was related to this one. What is the reason for taking number 80% and for the minimum state of health? Why not 70% or 50%, for example, SOH? So do we need to avoid overcharging and over discharging practical use for our battery to extend the battery lifetime? For example, we should stop charging 80%, showing the capacity or the mobile phone, and start charging before capacity 20% shown in the mobile phone. So there is why these specific numbers of 80 and 20, are they magic numbers, or do you think, Jürgen, there are some more scientific let me say, reasons?
From my point of view, it's no real scientific background. That 80% was the first mentioned by the American US EBC. They made some requirements for cells for electromobility. And they mentioned the depth of discharge, and the maximum should be no more than 80%. And again, that is by definition. And that number is going in the literature since that time, in all cases, in all meetings. And that 80% has, from my point of view, no real background. The background could be lower than 80%. The application conditions are no more given. So it could be, let's say, at about 75%. The safety of the system is so bad, so we could no more drive the car. But that is not the case. Even with 75%, you could drive your car, but the distance is shorter. And that is one reason why the car manufacturers and also battery manufacturers and energy suppliers use that battery after 80% state of charge for second use. That means for stationary application, for example, in your photovoltaic systems and so on. But the other way around would be you drive your car further with 75, with 70% and 60%, but your distance will be shorter. And I think so. From my personal point of view, if I had an electric car, I haven't in the moment, I have only a bike, electro bike, then I would drive further. So summarize, there is no real background for that 80%. And think a little bit further. If we reduce that limit to 75%, how much energy, how much money we could save. And therefore, that is also a very important question to discuss, that 80%. And from my point, to reduce that to 75 or lower, or to have a brighter range of that final charge limit or battery limit, lifetime limit.
Yes, if we could extend this limit, enlarge it, of course, we can save a lot of money, and maybe sensors can also be useful in this sense, most probably. Hope so. Okay, there's another questions again related to the parameters like SOH, SOF, SOE, SOP, SOC. How much these parameters are relevant to an end user? Because I can understand SOC and SOH that may be relevant during its use and for the second life. But what about the others like SOF, SOE, SOP? Does it help only with the research point of view, and how? So do you feel that for practical uses together with SOC and SOH, the other parameters can be useful or not? Or how?
Yeah, shortly only from my side, the state of function could be a practical parameter because for me as a driver, it's not important to know the state of charge and the state of health. For me, it's important how many kilometers I could go. And therefore, the state of function related to the kilometer, it's okay. The state of energy and the state of power make more, let's say, sense from the scientific point of view, not really from the practical. But we have to ask our other colleagues in the project, maybe they say any advantage from the practical point of view.
Maybe tomorrow, or if maybe Inigo is here, I don't know, or no, there's also Michael. Inigo, if you can add something on this point, if you want, as you are also here, if also other parameter like state of power, state of energy can be useful by a practical point of view. Maybe this is also a question I can keep for tomorrow, eventually to add after the presentation that we will have tomorrow. There were also something about, okay, the question was also if you can explain more about the volume changes in the cathode like NMC, LCO. Can you please clearly define lithium plating?
Yeah, the volume change in the layers material, it's let's say it's relatively clear. If lithium is coming between the oxide layers, so the gap between the layers is increasing. So that is clear. Then we have the other materials, the olivine structure. You have shown that the LFP, that is not a structure. It is not a layer structure. That is a more a solid structure. Let's say if lithium is intercalated, and that is not like the layered material. The oxide layers are the distance between the oxide layers are increasing because that is a 3D structure. That structure is from the volume side more or less constant. So that is the difference between both. And for all layered material, we will find volume change.
Yes, we can. In the case of LFP, the lattice is rigid. Like you can imagine, like a sort of shelf with defined floors where you can put your books, for example, or you put your lithium ions. But if you have a layer structure, in order to insert lithium between layers, you have to increase the distance between layers. About lithium plating is the reduction of lithium ion inside the layered structure of the anode. Commonly, the lithium plating, you have lithium plating at the anode where you have the reduction during discharge. So you have lithium that reduces and forms metallic lithium inside graphite. So this is lithium.
But only if the potential,
Yes.
the charge is lower than the lithium potential.
Yes.
If we have that charge and then we stop the charge coming in the open circuit potential, then the potential is coming to higher values like lithium, 0 point something, and then a part of the plated lithium is intercalated normally in the graphite because you have the higher potential.
Yes, and in this sense, sensors that can measure the voltage of each of the two electrodes will be very important, as you really see the voltage of each of the two electrodes, because what we are measuring is the difference in voltage. If the difference in voltage is so if the voltage at the end is lower than 0, as Jürgen told before, you have lithium plating, but the difference in voltage can be the same, can be even 4 volt, let me say, no, that we can go a little bit higher, 0.2 to 4.2, or from 4 to 0. And in this sense, we have still 4 volt, but in that case, you have lithium plating in the second case. So then there are again questions about the safety. In both cold leakage and fire, how much HF, hydrogen fluoride, can form? Is there any correlation between capacity of the cell? Is there any correlation with capacity, sorry, of the cell? So in both cold leakage and fire, how much HF can be formed, and if there's some correlation with the capacity of the cell?
It's a very difficult question. Normally, in the cold leakage, you have only a small amount of HF is generated, caused only by the by the water content of the air, so by the humidity. Therefore, it's not a big problem. You have to open the windows. That's more or less all. If you have fire, there are very different literatures citations. One mostly is coming from our Swedish colleague. She found a lot of HF in the thermal runaway gases, and other Japanese and American colleagues found nothing. So, and I know the Swedish colleague and the American and Japanese, they are serious researchers, both or all three. And the problem could be in the excitation, how that cell is excitated or is coming into the thermal runaway. For example, I have shown the example of the heat relation rate for NMC materials, which has a very high heat relation rate, and LFP a lower one. So that excitation could be play a role, and also the analytic one. In our lab in the ZSW or Nuln, we used to collect the gases from the thermal runaway. Oh, what is this in English? A glass mouse. Is anywhere could translate that? That is a that is a we call that glass mouse. That is a
No.
we put the gases in the cylinder, and that cylinder was closed on both sides. So, and with this cylinder on both sides, we went to the analysis equipment, and if that glass mouse or the glass cylinder was closed on both sides was storage for 2-3 days, we found no HF because the HF has to react with the glass.
Yes,
so,
yes.
So, and so you have two influences, one in the excitation and the other one in the analysis. And therefore, we need really good standards, which we haven't in the moment, to give clear information about the HF content which is involved in the thermal runaway and in the cold leakage.
This is something Michael is also reporting, that this is something that they are investigating into the cell integrated temperature sensor. So tomorrow maybe we have additional info about this. Then there's another question. There are many questions, and it's very good. We have still some minutes. Temperature mentioned for thermal runaway. I guess it's the actual temperature, but how it should be read for skin temperature?
Good question. Maybe the other colleagues which are working with the temperature sensor could give an answer. Normally, the core temperature is much higher than the surface temperature. And the surface temperature mostly is measured and the collector and the taps, because you have a good temperature conductivity to the tap, to the metal. But maybe the other colleagues could give some
In fact,
addition.
Michael tomorrow should give more info. Then, okay, Michael, as you are here, do you want to add something or not?
Yes, I could comment on this issue.
Thank you.
To be honest, I cannot add more than you already introduced. So I will give a presentation tomorrow on the integration of temperature and pressure sensors inside the battery cells and on the special requirements that come with this task. And I would be happy to answer further questions tomorrow after my presentation, and then looking forward to the discussion.
Very good. Thank you very much. There's another question related to why the trapped lithium in SEI cannot be compensated by lithium from the electrolyte. Don't know if you want to add something or I can answer too.
Because the lithium in the SEI, that is fixed. That lithium is no more free conducting, and therefore it could be not compensated by lithium ions from the electrolyte. But there is the other method. Free lithium, metallic lithium, could be integrated in the anode. So that is a pre-lithiation of the anode, and in that case, the lithium loss in the SEI could be partially compensated. Could be not compensated by the lithium from the electrolyte, but by additionally lithium in form of pre-lithiated anodes, that could be possible.
What is done, that one of the issues is also related to the fact that we do not know exactly how is thick the SEI. And then it can change depending on the additive in the electrolyte and so on. And when you are building a cell, you have to compensate to balance the capacity of the cathode together with the capacity on the anode. If partially the anode is, the capacity of the anode is lost because of SEI formation, of course, you have an extra, let me say, you are losing some of the total capacity of the battery. This can be somehow considered before during building the battery, but not completely. So even if lithium ion are more than enough, the one that are inside the electrolyte, but of course one lithium ion is fixed in the anode depending on the capacity of the anode. You need 6 carbon atoms per each lithium ion. If you have not carbon enough, graphite enough, you cannot insert additional lithium, and some of this capacity is fully lost. So I don't know if this was related to your question. And finally, there's a question, why does self-heating happen in the cell?
Again, could you repeat that?
Sorry, why does self-heating happen in the cell? This is last question we have.
Yeah, I've shown we have 3 basic exothermic reaction. One started at about 120 centigrades. That is the decomposition of the primary SEI. The second one, about 200 centigrade, that is the decomposition of the cathode material, this generation of oxygen. So, and if you reach that temperatures outside, for example, in arc heating up, or inside by higher loads and so on, then this reaction started and generated heat. And that generated heat is measured as the heat glow in an arc measurement, and also in the DSC you could see that.
I don't know if there are some additional questions related to the state of batteries. There are some questions also on the mechanism of working of a lithium-ion cell. I don't know if during the second presentation it was a little bit more clear. And there are also questions related to what is the cause of capacity fading in the battery. Of course, this depends on many mechanisms, as already Professor Garke told, and this is related to the state, the ACI formation, the temperature of where the cell is working. In general, you have an increase of resistance in the cell related to the degradation of electrolyte, and so the mechanism are really a lot. I don't know if you have something to add.
The active mass losses are caused by the resistance, but you have explained that already. Yeah.
Okay. Yes, so there are a few questions like if it was possible to have the presentation and if it is recorded. Of course, the presentation will be available. I don't know if they will be directly on the SENSIBAT website. And then also tomorrow, the course will be recorded and will be available. I think most probably this is something that we have to discuss, but it will be for sure on the SENSIBAT project website, and also I think on Battery 2030, maybe linked to SENSIBAT. Okay. Can you get a link? Yes, but we will do tomorrow with both of the presentation for the link for the recording of today. Okay, so I think more or less we answer all questions, because one of the questions were already a reply of something we already discussed about the expansion of structures. If there are no additional questions, I thank you all. I thank you in particular the speakers, Professor Garke, Daniel Brandl, and I really invite you for tomorrow. We will start again at 9. And we will go deeper in the use of sensors in order to measure the battery state and some practical applications. So see you tomorrow, and thank you very much for attending. Hope everything was went well. Thank you again. See you tomorrow. Have a nice afternoon. Bye-bye.